Hello, my name is Dr. Chad McGee, and today I wanted to talk a little bit about quantum physics with you to get kind of an appreciation for how I see the universe. I look at things a little bit differently than the average scientist. For example, what most people consider light isn't quite actually how it fits. For example, most textbooks teach you that light is a wave, like this. That's a flat plane wave, and that's wrong. For example, this we would say is two-dimensional. In reality, what light actually is more complicated, okay? Now, this gets into some little tricky things, because to be able to teach you this, you might actually need something from your household. In fact, most people would consider this garbage, but I think it is a teaching tool. This is a roll off of a roll of toilet paper, okay? So you can think of this cardboard piece as actually something that's teachable. And it turns out that if you look at it, it has a spiral, okay? This is the inseam that basically is how they make this roll. And so if you take that and look at it, you notice that it kind of gives a familiar shape. If you flatten this out, you'll notice that it does this to it, okay? That spiral part becomes like a wave. And so what I wanted to point out is if you can get a hold of a clear tube and draw that spiral around the tube, you'll end up with something more similar to like this. This is how I perceive light, okay? Light is actually a spiral bent around a tube. So it's not the wave as what they particularly see. We need to switch this up a little bit. It's more of a tube that has the light vectors bent around it, okay? So I'm going to go ahead and do the dashes as being the outside parts. Okay, that's basically spiral towards us. This would be the ones that are pushed away, and these are the ones that are closer towards us. So in reality, light is more similar to something like this. Now, of course, we know that light energy is actually electromagnetic energy. So we have an electric component and we have a magnetic component. So I'd be amiss if I didn't bring that up. So what I've done to show that part is I've got one cylinder where we have this blue vector, which represents the electro component, and I have this cylinder that has a yellow band that represents the magnetic component of this. Now, we know that these guys are offset by 90 degrees. So therefore, when you put the two together, you get this, okay? And so in a nutshell, there is what your light actually is, similar to that theoretically. This is the three-dimensional model of light, okay? So I wanted to say this one exists as the three-dimensional model for light. Now, why is that important? Well, I'll explain why. Because typically when you consider light as a wave only, two-dimensional wave, or if you want to consider it as a one-dimensional object, okay, then you run into this cross of duality, okay? Is it a solid ball? Is it going to act more like a wave? This circumvents that, okay? When you look at this way of reasoning, you have both at the same time. So this is what actually means by the duality, right? Case in point, this leads me to something that's quite valuable, and this is an argument on what creates matter and what creates antimatter. Okay, how is it created? What's the difference between the two? That's one of the biggest problems that's faced physics in a long time. We all know Einstein's famous special theory or relativity equation, this guy, okay? Of course, it comes from mass is equal to E divided by c squared. We're familiar with this, okay? So this one is the derivative of that part, all right? Now, what does it really mean? Well, what it really means, in a nutshell, is you take this electromagnetic energy and you can make matter or antimatter with it. But the question is how. That's the part where it gets to be kind of complicated. Now, a few years ago, well, actually many years ago, 20 some odd years ago, they came out with the concept of string theory. And string theory basically said that matter and antimatter were composed of packets of electromagnetic radiation energy that was basically acting like a string. So you could think of it kind of like this rubber band. It was vibrating and doing this, and you had multiple components to it, so they tie together, and then you had quarks and this and that, and you had gluons. Okay, that's all nice and neat and everything, except there's one big piece missing to string theory. Why it doesn't work the way it's supposed to. And that is, they've totally forgot dimensionality vector. Light always has to have a momentum vector. If it doesn't have a momentum vector, that means it's stopped and it no longer exists. This is a key component to why we have matter and antimatter as this form. Now, this leads to my correction of string theory, and that is you have to have a directionality vector included in with it to make it go. So I call it a ring-coiled theory of string theory. That's the correction part to it. So, in a nutshell, what is matter? Okay? Well, case in point, I'll talk about how do you make matter from this light energy. Okay? We'll go into that detail first, and then we'll go into what does this actually mean. From this piece here, we can see that the light is coiled around, and if you take light and interact with something in such a particular way, this can potentially bend upon itself. If it happens to coil in the same direction that it was coiling in and completes a circle, okay, that would be matter. For example, in this particular case, this would be the simplest one, and this would be an electron. One simple loop is an electron, and that would be a formation of matter. Now, antimatter in this form is a little bit different, okay? Consequently, that leads to this little big discussion we have, is when you look at the universe, you don't see a large amount of antimatter, you see lots of matter. Well, the reason why is it's much easier for this to bend upon itself when it's already curved that direction. To make antimatter, you actually have to bend it the other way. Okay? So the net effect from that is you get this. Okay? The net effect is essentially the light will bend the opposite direction. The light momentum vector is opposite of that. Right? And that means that you're going to have similar properties, yet opposite charges. Okay? So in this particular case, we can say this guy is an electron, and this guy is a positron. Now you're probably wondering about the charge, and I'm glad you asked. The reason why charges come about has to do with what we call the net momentum directionality. If it ends up having one loop, and it is specific for directionality, whether it goes towards this way, okay, that becomes a positive, or so that becomes a negative value. If it goes the opposite direction, then it becomes a positive value. That's why a matter piece, like an electron, in this particular case, it has that directionality that gives it a -1 charge. But when we reverse that, we make the antimatter form, which gives it the positive charge. So this is the positron, this is the electron, and consequently you can see the differences between the two. Okay, now where does all this energy go? What does it do? Okay, this energy, this light energy, is actually still there. Okay, it actually forms the ladder, and you're probably looking at this and going, wait a second, this is a bit different than what I learned in Gen Chem. Okay, you're used to seeing electrons as paired. Okay, maybe you said spin paired and stuff like that. Okay, and maybe you drew an orbital set, and maybe you drew something like that. Okay, or maybe you drew a ball. Well, all those are representations of it. I'm looking at this as if you could take an atom, and essentially freeze it instantly and look at an electron from that atom, this potentially is what you'd actually see. Now, granted, take into account, this is the electron portion, so the magnetic portion would be this way, okay? This is the magnetic, and that forms the magnetic fields in each electron. All right, so that leads into kind of some interesting discussions, because what would happen with this guy? Well, of course, the magnetic field is going to be opposite of this. So you're going to have some directionality differences. They're similar, but yet opposite. So that kind of leads into some discussions. Now, where does all this energy, what does it do? Well, in actually taking and making matter and antimatter, the energy itself is transformed into the properties of said matter and antimatter. And so what Einstein was after in this famous E equals mc squared equation, there's actually a little piece missing to it, okay? And that is, there is a relationship between the properties, okay? So in other words, you can look at that as the sum of all the properties of the matter and antimatter is dependent upon the energy that was formed from, or was used to make it. So that's a kind of a key component that I wanted to bring up. I think at this stage that's enough for today to let you kind of mule over, and then we'll meet again and discuss more. Now the next one I'm going to talk about is moving up from electrons. Let's go to quarks and see what a quark is, because quarks can be rather interesting materials to look at. Thank you.